So skeletal system. Now we're talking about bone. So what category of tissue are we going to put bone in? Connective tissue. It is a specialized connective tissue. And without bones, your body wouldn't be very good at moving. So, are bones essential to movement? You got to say yes. Bones are essential to movement. Are bones the most important thing as far as your body moving? No, because if you got bones and nothing else, you know, it's not going to happen. What else do you have to have with our bones? Muscle. And specifically, what kind of muscle? Skeletal muscle, because it's attached to our skeleton. So again, as we look at our skeletal system, we haven't put our muscles in here yet. So we can talk about the bones. We can talk about ligaments. Again, ligaments connect bone to bone. And then we talk about our cartilage. These are going to be parts of our cushion system that we have. And in fact, when bones develop, many of our bones start out as cartilage. And then they turn into bone. Except for one very important part, I think growth plate we've already heard about. That growth plate is still growing cartilage, and that's what allows your bones to extend until you're about the age you are right now, in which case that cartilage in your growth plate all becomes bone. And that's why you don't grow any taller, your arms any longer, typically, because those growth plates have all undergone the process of forming bone. All right, so what do bones do? And we got that one, right? Support. Sure. You wouldn't be able to stand up. Okay. You wouldn't be able to not worry so much about your lungs and your heart, right? What protects your lungs and your heart? Your ribs, bones. The poor guy you took out, unfortunately, there was a bone that protected his brain, but it didn't work so good. What protects your brain? The skull. You finished the quarter. Did they let him go back in? Did he know his name? No. Movement. We got movement, right? Think of the bones as the levers. And think of the muscles as the engines. They get movement done. So bones are going to be the levers that allow you to get the work done depending on how the muscles are pulling on those particular bones. All right, we've got our protection. We've already talked about it up there with support. Formation of red blood cells. Where in the world do red blood cells form relative to the bones? In the middle. In the middle of the bone we call the marrow, and we're going to see that in some illustrations that we'll get to shortly. And then lastly, bones are where you store minerals. And the principal mineral that's going to be stored in your bone is calcium. Bone is a calcium phosphate matrix, but it's the calcium that's absolutely critical. There used to be old commercials that would come on during the cartoons. Milk, it does a body good. You remember that when you were kids? You might still be too young for that. But it was getting at, okay, you need strong bones. But is calcium just for bones? No. As we get to muscle, and we look more in depth at muscle in the next chapter, muscles will not contract without calcium. So you got to have it for muscles. You got to have it for bones. In our picture of our neuron, you know I said the neuron will send a signal and will pass that signal on to the next cell. You can't pass the signal on to the next cell without what? Calcium. So nervous system's not going to work without calcium. Man, there's not much left. Calcium basically is needed for all cells and all tissues. So this mineral storage is important. And if you don't get enough calcium in your diet, your body is going to sacrifice your bones to make sure your other tissues and your heart and your nervous system has plenty of calcium. So it will rob that calcium from your bones and your bones will become brittle. That's how important that is. All right, so let's do a little anatomy. And we're going to start looking at our long bones. And when we say that, they're longer than wide. So this is going to be like our legs, our arms. And so if we start on the outside, we have a connective tissue. This is going to be a fibrous connective tissue. This is going to allow our ligaments and tendons to attach to one another, because remember, they're connective tissue as well. And that outer connective tissue covering is called the periosteum. Peri meaning around. Osteum or osteo refers to bone. You know the disease osteoporosis? Have you ever heard of that? Usually happens in elderly individuals, typically elderly females. What happens to the bone in osteoporosis? It gets very thin. Actually, it gets filled with holes or pores. Do you see where they get the name now? Osteoporosis means porous bone or very brittle bone. So osteo means bone. Now the main part are the shaft of the bone. The longest part we call the diaphysis. And on each end, almost like the ends of a Q-tip, we have sort of these rounded regions, and these are called the epiphyses. And in the middle of our diaphysis, and even to a lesser extent in the middle of our epiphyses, we have a hollow central cavity that we call the marrow cavity. And typically it is going to be filled with either yellow or red marrow. Now, can anybody guess what those colors signify? If I'm red marrow, what do we have a lot of there? Red blood cells. If we're yellow marrow, what do we have a lot of? Fats. And if you have a dog, and that dog loves to gnaw on a bone, it's not that the dog likes chewing on the bone just to be chewing on the bone like a baby teething. That dog is trying to break that bone open and get to the fat inside of the marrow. And once that dog eats or licks all that fat out of that bone, he's done with it. You better get another bone, because that's the rich, fatty part that dog is wanting to get to. So here's our illustration of a long bone. We can see our diaphysis, most of this shaft. We have an epiphyses at the top, and even though they didn't label it, this is an epiphysis at the bottom as well. And as you see sort of in the middle, this almost pinkish looking layer that they folded back, they're trying to illustrate the periosteum that goes all around the extent of our bone. Now that's what the bone looked like on the outside. But if we could cut the shaft in half and look at the cut portion of that bone, we would see that there are two different arrangements. Not necessarily so much types, but arrangements. The hard, solid part of the shaft that's on the outside, we call that the compact bone. And toward the inside, as you get close to the marrow cavity, and especially in the center of these epiphyses, we have what's referred to as a spongy bone. You know when you look at a sponge, like you used to clean the dishes or clean your bathtubs, that sponge is almost more holes than it is stuff. Well, in this case, our spongy bone is going to be that way. We're going to have these shards of bone that are separated by a lot of porous spacing. And that porous spacing is going to be great for a lot of cells to crawl through and get in between. It's going to be a great place to have a marrow cavity. So here on the outside, this is our periosteum that we see in this illustration on the left. It's been folded back. Here you see a lot of blood vessels and nerves coursing through our bone as well. But you see how there's very little space in our compact bone? At this point, don't worry about the birthday cake. We'll get to that in just a bit. But that is our compact bone, very strong on the outside because your bones have to support the weight of your body. But then as we move toward the middle, toward our marrow cavity, do you see all of a sudden we have all these spaces? And it does kind of look like a sponge. More space than you have actually bone. And so that is our spongy bone more on the inside. We're still going to have quite a bit of strength because of that bone, but it's going to be lighter. It's not going to have as much weight. Now, for humans, that's not really important. But for birds, it's absolutely important because birds have hollow bones to save weight, because the more weight you have, the harder it is to fly, and the more energy will be required. We talked about the different types of bone, sort of generally speaking, it's how they're constructed. We have the compact bone and the spongy bone. Well, we're going to look at the compact bone first. This makes up the outer part, the strongest part of our bone. And what we're going to see, it's made up of these concentric columns of cells and calcium phosphate bone matrix. And this functional unit's called the osteon. Now, if you recall, last time we saw a picture and I said, don't worry about the wedding cake looking thing. Do you remember that? That picture there, I showed it to you again because I probably wouldn't remember it either. In this illustration, what they have done is they have taken an osteon, and we can see there would be one in the foreground here, one in the foreground. And what they've done is they've taken each one of the layers and raised them up so you can see the concentric ring nature. Do you understand what I mean by concentric ring? It's like the layers of an onion, or those little Russian stacking dolls, one within another within another. And so in the very center of our wedding cake osteon, we have a canal, and that's where our arteries, veins, and nerves are going to be running through these openings. It's called the central canal. And most of what you see in this area that we have bracketed as spongy bone, this yellow brownish type material, that's not cellular. That's just calcium phosphate inorganic matrix. The little black, kind of fuzzy looking things you see, those are going to be the cellular part of our spongy bone. So we talked about the central canal, where we have our blood vessels and nerves running. The cells that look kind of fuzzy in that picture, they are called osteocytes. Now, once we get into pre-medical histology, we differentiate between bone cells depending on whether they are surrounded by bone matrix or not. For our purposes, we're just going to call them osteocytes. Osteo meaning what? Bone. Site is the word. This is a suffix for cell. So these are literally our bone cells. They're going to lay down that bone matrix comprised of primarily calcium and phosphate in those rings upon rings upon rings. Now, what I want you to appreciate here, cells aren't going to live if they can't get oxygen, if they can't give off carbon dioxide and other wastes. And what's a very important carbohydrate all cells are going to have in your body? And if you have too much of it, your body's going to store it. Glucose. So if cells have completely surrounded themselves by this essentially concrete wall, how are they going to exchange materials with blood vessels? Especially the cells that are in the far outermost ring of our osteon. Well, in old Western movies, when the barn, or let's say the church, it's usually the church. I don't know why they like to burn churches up in the old Westerns. But when the church catches on fire, how do they put the fire out in these old Westerns? You ever seen somebody grab a bucket of water? And what do they do with that bucket of water? They throw it on the fire, but they hand the bucket to somebody else and somebody else. The bucket brigade, handing the buckets down the line. That's how osteocytes operate inside the bone matrix. Because the cells that are closest to the blood vessel, they're going to pick up more glucose, more oxygen than they actually need. Because they then are going to hand the extra off to the cells that are down the line. They have these little tunnels through the bone, the actual hard part of the bone, and they're going to extend little cellular processes called canaliculi. And these canaliculi are going to connect up with the canaliculi to the next cell. And notice we have specialized junctions between the two canaliculi of the two different cells. What are those specialized junctions? What are those last two words? Gap junctions. Do you remember those when we talked about epithelium? What are gap junctions? Very simple explanation of gap junctions. What are they? Whether you're city or country, you know. Remember how we differentiated those? Culverts versus tunnels. And so if cell 1 has extra stuff, some of that extra stuff is going to make its way through these tunnels, the gap junctions, and into the next cell. That next cell is going to use what it needs, and guess what it does? Passes the extra on to the next cell, and on and on. And then we're going to do the reverse with the waste. The waste coming from the outer cell is going to be passed to the next one, and the next one, finally, the one on the inside, dumps all the waste into the venous supply. So do you see how all of our cells are in fact connected to the bloodstream? The first ones are directly connected, but the ones in the other layers are indirectly connected through the canaliculi. And that's what gives this sort of fuzzy look. And you see these little cracks, the little lines in our illustrations? Those are the canaliculi that are interconnecting this ring of cells to that ring of cells to that ring of cells. They're all connected within the same osteon. And it's because of those, all the cells in your bone are living. Because the bone is a dynamic tissue. It's always being remodeled. And we'll touch on that in a few minutes. Now, if we look at spongy bone, that's the bone on the inside, adjacent to the marrow cavity. In this area, we don't have a solid column of bone. We have all these little pieces. And remember, we almost have more space than we actually have bone. That's why it's called spongy, porous type bone. And so the little pieces of bone are called trabeculae, which if you translate the Latin literally, it means little beams. You don't sacrifice a ton of strength, but what you gain is it makes the bone lighter. And remember we said for birds, that's incredibly important if they are ever going to get off the ground and fly. So if it's lighter and it's as strong as the compact bone, then why do we have compact bone in the first place? Why don't we make it all spongy bone? Well, when you look at evolutionary history, something that has a survival advantage is going to be passed on to generation. But something that doesn't make a huge difference or it's not detrimental, it could just be preserved. And so in this case, compact bone on the outside is strong. We have plenty of energy to keep all those cells alive, and so it's not a disadvantage to survival. So we have kept it in the human system and in the human histology and anatomy. Now, since these trabeculae are so small, we don't have to have these concentric rings. All of these cells are close enough to blood vessels that we're not going to have that arrangement. And some of our bone cells are actually going to be sitting on the outside. And this is where there's a difference. This is a freebie, by the way. You don't have to write this down. But if the bone cell is not completely surrounded itself, it's called an osteoblast. And the B for blast, I say, is baby, because it hasn't grown up into the full one that's completely surrounded that becomes an osteocyte. So here we see a different illustration of both our compact and spongy bone. We see our osteon arrangement in the outer portion of our bone. That's going to be the compact. And then on the inside, this almost looks like a ladder of bone, but you can see all the spaces. That's the spongy bone, and each one of those little lines of bone that you see, those are the trabeculae. Any questions about compact, strong, heavy bone versus spongy on the inside? Simply, we're just describing the cellular anatomy of our bones as we begin to move forward and look at what the names of the bones are. But before we do, let's look at development. I'm an embryologist. I love studying how you go from one single cell into a baby in 9 months. Does that blow your mind? In 9 months, You go from one cell to a baby with all of these different cells and these different functions in different places. It blows my mind. And my specific area that I study is the heart. When we get to that part, you'll hear my energy pick up quite a bit. I just love talking about the heart. But bone's pretty cool too, because when we look at our bone, we're going to see that your bones don't start out as little models of themselves and just grow bigger and bigger and bigger. We start out in many of our bones with a template made out of cartilage. And the cartilage grows, and then the cartilage is replaced by your bone matrix in a process that's called ossification. And so if we look at this illustration, we might see a fetus 2 months after fertilization. And we've got this little teeny model of a bone that's completely cartilage. And then slowly, over time, we can see that blood vessels grow into that cartilage. Because remember, cartilage doesn't need a lot of blood vessels. There's not nerves in that. But as these blood vessels come in, they're going to bring stem cells that begin to produce bone. And the first place that those cells are going to produce bone is in a collar right around the middle of the shaft of the bone. Because cartilage, those cells survive by diffusion. And when you put that bone collar around there, what are you going to do to the cartilage cells? You're going to strangle them. You strangle them so the cartilage cells die, leave space, that then the bone cells come in and occupy. It's almost like an invading army, if you want to look at it like that. But the bone begins to grow, and you can see that here in our yellow-brown material. And then finally, as we get, newborn, early childhood, blood vessels grow into the ends of our bones. Remember, the shaft is called the diaphysis. The ends are called the epiphysis. And then we begin to see bone formed in the ends as well. But notice, we still have 2 bands of cartilage situated between the epiphysis and the diaphysis. And what's the name that we have right here? What's the name for those? Your growth plate. It's because you have cartilage, it gives your bones the ability to lengthen. And after about the age of 20, 22 or so, all of the cartilage in your bones, including those of the growth plate, ossify and become bone. That's why you typically do not get any taller after your early 20s. Your growth has stopped. But typically, if you have a younger person that injures their growth plate, if it's in one of the long bones especially, it is a huge problem, because if you damage that and the growth stops in one leg versus the other, I think you can imagine what's going to happen. You're not just going to have a limp, you're going to have a very difficult situation. So this shows we've got the epiphysis, and notice the size of the epiphysis doesn't change that much. But the length of the shaft of the bone, the diaphysis, lengthens and continues to push that growth plate upward. You're continually adding new cartilage to this. And as you add new cartilage, it's remodeled, reshaped. The cartilage dies, you add more bone, and it pushes the 2 epiphyses away from one another to lengthen our long bones. So here we are, and unfortunately, ladies, your bones typically stop growing a little bit earlier than males, biologically speaking. With this particular one, what I want to get at here, and when we say growth, we're talking about the length of the bone. But your bones are continually being remodeled. And this illustration is trying to show that depending on the forces that you apply to your body, your bone can drastically change its shape and its anatomy. And I go back to these Egyptian archaeologists. I love watching those shows where they're finding the pyramids and the new tombs and looking at the mummies. And probably a decade or so ago, they found an entire village of people that actually built the pyramids that lived, I think, just right in the vicinity. And they looked at all of the mummies of these individuals and their bones. And they could tell who were the workers and who were the elites of the day by looking at their leg bones. And here's why. Let's say you are a worker and your job is to carry some of these big, huge blocks. Or you're carrying rubble day after day after day on your shoulders, on your head. And so you've got a lot of these compressive forces that are pushing down on your bone. Well, when your normal bone has a bent shape like this, you're exerting more stress on the inside than the outside. So this repeated stresses causes your bone to be removed from the outside where there's not a lot of stress and new bone deposited on the inside. And notice how straight that bone is now. So by looking at the thickness and the direction of where that bone thickens, archaeologists can get an idea of how hard you had to work in your life. Now, this is not going to be happening in a week's time period. If you go out and you do some hard work on a Saturday one weekend, no, you didn't significantly change your bones. This is day after day after day, year after year after year, this repetitive motion. Now, we know the osteocytes, those are the cells that produce bone, that live in the osteons, that live in tuberculae. Well, the cells that remove the bones are called osteoclasts. They look like big amoeba that are sitting on the bone, and they actually produce acid and other enzymes that dig out little scoops of the bone. And then they move to the next spot and dig out another scoop of the bone. And they're continually remodeling this bone. And that's how we remove that bone in the previous slide from the outside by the osteoclast. And the osteocytes made the new bone on the inside to thicken that bone. So here's a diagram on the left. We've got 3 osteocytes here. These 3 osteocytes in the back, they're just landing on the bone. But do you see over time how they form these little depressions, these little pockets into the bone? Here's another freebie. It's one of my favorite terms, and I don't know why. In histology, these depressions are called Hauschup's lacuna. Hauschip, I guess, was a guy's name, and a lacuna is just a sort of a generic name for this little depression. This is a scanning electron micrograph that shows the surface of bone, and this is an osteoclast, and it's detached from the edge of the lacuna, and you can see how it's already beginning to etch the bone underneath with that acid and with the enzymes that are removing both the organic and inorganic parts of the bone. Now, my histology students, they look at stuff like this. This is an actual histological slide showing bones. You see you've got these little spiny things here? That's an osteocyte. These are some of the canaliculi. And there's a big osteoclast, multiple nuclei, and that's one way you can identify these big cells. And you see this sort of curved depression? That's typical of the H for the Hauschup's lacuna. So that's how your bone's getting remodeled. Cells dissolve it, and cells put it down. Now, that may be a bit more technical than what you as non-science majors really bargained for in a human biology class. Are you ever going to have to worry about anything like that? Guys, you probably don't have to as much. Ladies, are you going to have to ever worry about osteoclasts? When you get older, why? Remember we talked about osteoporosis last week? Osteoporosis, scientists have found that changes in the hormone level at menopause cause osteocytes, the bone depositing cells, not necessarily to slow down. They stay about the same activity-wise. But guess what happens to the osteoclasts when your hormones change? They go through the roof. So you're removing way more bone than you deposit. Now, what's one way that television and natural food places, they try to get you to offset the bone loss? What supplement do they want you to take? Calcium. I want you to take calcium. Take more calcium, strengthen the bones. What's the problem? Your osteocytes are not going to work any faster. Calcium's not going to slow down the osteoclasts. So that's why it's important, especially post-menopausal, you need to have your hormones balanced. Now, a lot of primary care doctors, they're just going to throw you on birth control pill. And when you're menopausal, it's kind of like, why in the world would I need birth control if I'm post-menopausal? So you need to go to an endocrinologist. You need to have someone really work at balancing all the hormones in your body, especially the estrogens. Because if you try to balance the estrogens so that you can get the osteoclast to slow down, and so you get a lot more estrogen, guess what you've just increased your risk for with more estrogen? Breast cancer. So it's not an easy fix. And guys, we'll get to the stuff that we have to deal with too. So you just wait your turn. But that's why it's important to take care of that. And it's why it's important to know, even for a novice biologist, to have some idea of the human body and how these things happen, because guess what? It's going to affect every single one of us. All right? So we've talked about our long bones. Now we're going to talk about the connection between our bones. Now, two categories of these are going to be, one's going to be between our long bones, and we have two other categories that maybe you don't think about as much. We're going to save the junction between our long bones for last, and those are our synovial joints. But we have fibrous joints and we have cartilaginous joints. And again, we sort of simplified this terminology a little bit for this class. But I want to take each one of these three and give you a little bit of deeper understanding about their functionality and, what are they good for. Now, fibrous joints, we're going to touch on those first. I'm not going to say that these are the most important. And in fact, when you see this immovable word, does that really fit in with you, or does it seem like an oxymoron to say immovable joint? I thought joints were movable, right? Well, these junctions are between two bones, and at one point, there was movement that was allowed. But then as you get older, these joints fuse together so that there's only one faint line that indicates that there was a joint there to start with. And these are going to be the flat bones of your skull. Each one of these bones of your skulls are not attached to each other. The bone is not locked into bone. And in fact, you know that too if you have ever held a baby and you felt this spot. What do you call that? The soft spot. You have several of these fontanelles, which are actually at these intersections of these bones, which create a spot. This is just the biggest one, and that's the one we call the soft spot. Why on earth would you have a baby whose skull bones were not completely fused together before they were born? Why in the world would you not do that? You want the baby out, right? So the reason that these bones are not fused together before birth is the bones have to deform. And we all have those family members, friends, that have that beautiful baby that's got the what? Got the cone head, right? That uterus has been pushing that baby's head into that birth canal for hours, and that heads and those fontanelles have reshaped and slid, some kind of slide over each other, to fit through the birth canal. But what's the good news about the cone head baby? You don't have to live like that forever. And there are a lot of women now that are electing to have C-sections just because they don't want their baby to have a cone head, which is crazy. Now, if I were female, I would be having a C-section for a whole different reason, and I would be wanting a C-section about week 4. Because I'm a wimp and I'm not going to go through it. No. I admire ladies that go through that and still love their children. And after this class, you need to call your mother and say, I'm so sorry. But do you see the significance, though, why those bones cannot be fused? They have to be movable. But then after birth and through childhood, the bones fuse together, and all you see are these kind of squiggly lines that are called sutures. If you ever look at a skull, you can see those lines, and those are the fused parts of those bony plates that became immovable during your childhood and even on into adolescence. So this is from the top of the head. We see our frontal bone, that's a frontal suture. This is going to be our sagittal suture, and sagittal just means right down the middle. And here in the back, we can see we've got our parietal bones on either side. This is our occipital bone. And then you don't have to know these names. I'm just know sutures, know what the sutures are. I'm not going to ask you all these bone names. Not from this illustration. But you see the sutures now? Did you ever wonder what those lines were? Now you know. Right, our second type of joint, cartilaginous joint. These are going to allow a little bit of movement, but not a ton. And the cartilaginous joint that we're going to talk about are going to be your intervertebral discs. These intervertebral discs largely have this fibroelastic cartilage that has this kind of jelly-like center to it. And if you've ever had someone that had a pinched nerve or were having back pains, they either had a ruptured or a slipped what? Disc. That's what we're talking about. Now, a slip disc just means this whole thing moved. And if it moves forward enough, it's going to start pushing against that nerve. That's not going to be fun, right? A ruptured disc is where this outer fibrous part splits and allows some of this jelly-like center to rupture through and push against the nerve. Either way, it's painful. It's no fun. These, so far, we don't have the technology to replace. At best, doctors can go in and shave some of this off, but what's the danger in this? What are you very close to? Yeah, you're very close to a nerve.
So what do they do, like, if that jelly stuff is like?
Well, one thing they can do in very severe cases, they can come in and they can fuse these two bones together so that the space doesn't get less, and so you're not going to compress any more on that. They'll trim as much as they can, as delicately as they can. Sometimes they will put a metal rod, and they'll anchor a metal rod here and a metal rod there, and that will keep the vertebrae from pushing down. Now that's extreme, but I've never had that kind of back pain, but a lot of people that do, once you have surgery, typically you're going to have pain the rest of your life. It may not be as bad, but protect your back, right? How are you always supposed to lift an object? You bend with your knees, keep your back straight. Don't ever just bend over and lift up. That lower back is where you will pop it every single time, all right? And the best thing to do is if you have to lift something heavy, pay somebody else. Or offer, free beer to your buddies. That pizza and beer usually helps people lift stuff. That's like some magic ingredients there. Now, the joint that we are most familiar with, and these are our fairly movable joints, these are called synovial joints. Has anyone ever heard of a joint capsule or had someone that ruptured a joint capsule? They had arthritis or swelling, like in your knuckles or your fingers. What's happening is around the ends of your bones, you do have this membranous capsule, and on the inside you have this thicker kind of fluid that is called synovial fluid. And this synovial fluid works again like a hydraulic sort of compression resistor or a cushion. You're not going to compress this any more than you necessarily would. And so in this particular arrangement, we have this fluid-filled capsule. And this could be your knee joint, your elbow, Those are two places we have these synovial joints. And really it's going to be where you have bone-to-bone connection. So we've got our ligaments that are helping secure that, like our ACL, our anterior cruciate, our MCLs in our knee. But we also have muscles attaching to the bones via tendons. Now remember, our tendons and ligaments, they're made of that same dense connective tissue, almost pure collagen. And honestly, the best way, if you want to prevent having a knee injury, the best thing you can do is make sure your leg muscles are in the best shape possible. Because the muscles and the tendons help support and stabilize the knee almost as much as the ligaments do. Which always amazes me because our professional athletes are some of the fittest people in the world, and yet we're seeing them tear stuff up all the time. But I'm not going to try to cut, and I'm not getting tackled like those guys do. So they're having some extreme pressure put on those joints when they blow them out. Normally, we're going to be just fine with the arrangement of our body unless we do something stupid. Isn't that usually when we tear stuff up? When we do something stupid. All right, so everybody recognize this? Everybody know what this joint is? It's your elbow, right? No, it's your knee. The patella is kind of a giveaway. So here we're seeing some of the ligaments, and here's our anterior cruciate ligament. It starts in the front on your lower bone, and it goes underneath, and it attaches sort of on the dorsal surface of the back of the femur in this connection. Now, you see the blue? The blue that's covering the femur and the blue here that's covering the tibia. That's cartilage. That's going to be a low friction surface in here. But we're also going to have a capsule that completely surrounds this, and this whole area is going to be filled with fluid. And so the cartilage and that synovial fluid that's going to be between your femur and your tibia, that's going to have that sort of cushion effect. Have you ever hydroplaned in a car? Your car, and the way that you're suspended on a layer of water. Well, in this case, your femur largely, the majority of the time, is going to be suspended on a layer of synovial fluid, and it's never actually going to touch the tibia. Now, when you get older and you start having arthritis and you lose the cartilage, then you're going to get bone-on-bone contact, and apparently that's some of the most excruciatingly painful types of feelings you can have. All right, so we spent a lot of time talking about our knee and our elbow. Those synovial joints are your hinge type joints, like the hinge of a door. You know, you can open it and close it. But we also have synovial joints that are ball and socket joints. When we look at the head of the femur, which is your lower leg bone, it's got this big, huge ball. It sets into the socket of your hip bone. It's called the acetabulum. We also have the top of our humerus. We have sort of a rounded surface, and that's going to fit into the fossa of your shoulder blade, your scapula. Well, those are going to be surrounded by membranes. Those are going to have fluid within them. And so those are examples of our types of synovial joints that we have. Now, we got a lot of people in here that's done this, right? Sprains. We had a couple of tears too, right? So a sprain is where you unduly stretch a ligament or a tendon. And of course, we do have some nerve endings there, and it's going to remind you, okay, you did something you weren't supposed to. And if you sprain something, yeah, you can ice it. Yeah, you can take your ibuprofen. But what is the only way to get over a sprain? Rest. That's the last thing we want to hear, right? Stay off of it. No, what's another option? No, that's it. You've got to stay off of it. You have to rest. Now, what they're finding more and more, that resting, staying off of it, means you don't exert yourself the way you did when you sprained it, but actually light mobility is good. You don't need to be completely immobile with a sprain, but you've got to take it slow. Now, you sprain it, you got to rest. You tear it, how you going to fix it? Call the surgeon. Right? We've already talked about the fact that your body's not going to heal that on its own. You got to have surgical help. All right? Does this number surprise you at all? That you have 206 bones in your body? Now, that number, can be plus or minus depending on which bones you're counting actually. Some like to group some smaller bones together, but we're going to stick with 206. And we can divide the bones of your body into the axial skeleton or this big, huge word called the appendicular skeleton. Now, when you think of an axis or an axle, what picture comes to your mind? An axis or an axle, what comes to your mind? The what? The globe. What's the axis? What? This stick that runs through, right? North to south. This line. Axle of your car. This line that goes from wheel to wheel, right? So when you see axial skeleton, it's this straight line up and down the body. Your vertebrae, right? So our axial skeleton is just everything in the straight line. So if the axial skeleton is up and down, what's the appendicular? Everything else. See how that works? Isn't that cool? Could you go get that door for me? So our shoulder blades, our pelvis, our arms, our legs, that's all going to be part of the appendicular skeleton. Just two very broad categories of bones and how we can group them together and understand where they are in the body. Now I said we were going to start simple and build, right? Okay. Axial, straight line. It's composed of the skull, which we already know has a bunch of bones. Our vertebral column, backbone, composed of each one of our individual vertebrae. Since they're attached, they sort of get honorary status as part of the axial skeleton, but our rib cage, they're attached to our vertebrae on the dorsal surface, but on the ventral surface, what do our ribs attach to? What do you call this? What's the common name? Breastbone. Your breastbone or the sternum is connected here on the ventral surface. So those are the big components of our axial skeleton. All right, so skull. 24 bones. We're not going to name them all. We're not going to be able to identify all of them. But some are pretty easy, like your forehead. Is this the front or the back? Guess what its name is? The frontal bone, right? Isn't that great that they do that? When your head's hurting over here on the sides, what's hurting right there? Your temples. Have you ever wondered why they call them temples? It's like, is some in church, a temple? No, the temporal bone is on the side of your head. That just leaves this big part in the top, which is called the parietal. I haven't figured a good way to remember that one. Or the one in the back. The one in the back is referred to as the occipital bone. No?
Occipital's eyes. The eyes are in the back of your head.
That is awesome.
That's what psychology
So but that's awesome because when we get to the brain, we'll see that the region of the brain that functions for vision is in the back. And so moms always have what? Eyes in the back of your head. I used to freak my kids out until they figured out there was a rear view mirror. Yeah, that's funny. That's good, but so we're left with parietal for the top. What's a good way to remember parietal? We'll come up with something. All right. So front, top, temporal on the sides, occipital is in the back. Remember, vision, eyes in the back of your head, occipital. Oh. No, that's not going to work either. Okay. Now, our jaw, the human jaw is comprised of two bones. We're probably most familiar with the bottom one. What's the bottom one? The mandible. That's the easy one. The one on the top sort of sneaks away from us because it is somewhat attached to the rest of the face of the skull, but we do consider that a separate bone, and that's called the maxilla. So the maxilla and the mandible make up your upper and your lower jaw, respectively. Now, we're looking at, we'll call this the bottom of the skull. And in terms of describing human anatomy, we always talk about superior being toward the head and inferior being toward the feet. So this is the inferior part of the skull. Here you're looking up at the roof of the mouth. Here you're looking up at the underside of the skull. And here in sort of the underside of the occipital bone, we have this big hole. A hole in biological terms is called a foramen. And what's a good word for big? Magnum. So literally translated, what does foramen magnum mean? It means a big hole. And that's what it is. Because what has to come through that big hole? Your spinal cord. The lower part of your brain stem and the spinal cord come through the foramen magnum. And that's just going to be that opening there in the occipital bone on the inferior side of the skull. All right, so we got the skull all figured out. Got the foramen magnum, spinal cord coming down. Well, the spinal cord is going to be protected by these individual bones that are lining up to form the vertebral column. And of our 206 bones in our body, we have 33 vertebrae. So what does it do? Well, keeps our head up most of the time in here. Sometimes y'all conk it over. Protects the spinal cord, and it's going to be a place where we can attach our limbs. Basically, we attach the appendicular skeleton back to the axial skeleton at the point of our vertebrae. So here are, in essence, our 33 vertebrae. Our neck vertebrae are said to be cervical. This is where you do not want to have an injury. Because as I said, coming through the foramen magnum is the lower part of the brain stem. And if you end up damaging a high cervical vertebrae, you could damage the brain stem. And if you damage the brain stem too high, your brain stem functions for breathing and for your heart rate. Guess what you're not going to be doing if you damage it too high up? And you're dead. That's it. End of. Damage it even further down, you're quadriplegic. So cervical injuries are bad. And a lot of those happen in the summertime, people diving into water and they're not knowing what's there. In a swimming pool, it might be too shallow. Around here in East Texas, rednecks jumping off into creeks and lakes, out of trees and all sorts of things. They land on logs and rocks, and it's a horrible way to spend the rest of your life. Now, as we move down from the neck, we move into the chest area, and that's called the thoracic vertebrae because your chest is referred to as your thorax, or the thoracic cavity. The smaller your back, lumbar. We're probably familiar with that one, right? The lumbar adjustments on your car seats. We kind of know where that is. Now when we get down to the back of the pelvis, the back of your hip bones, we have this almost pyramid-shaped structure that's referred to as the sacrum. Now these are 5 fused bones. Some people consider that one bone, some count them as 5 individually. And then the coccyx are these 4 small bones that are fused together into your tailbone. And if you think they're insignificant, break that sucker. Yeah. Be in that cast for 4. It's not a cast. Now, don't forget, between our vertebrae, we cannot have bone on bone. That's going to be painful. So we have our fibrous cartilages, our intervertebral discs, that are going to cushion the junction between those vertebrae and allow us to have some flexibility. That's why we can bend laterally, side to side, and we can bend forward and we can bend back, but there's a limit to that. That's because those shock absorbers, those cushions, are only going to allow a certain number of degrees of freedom. And then we have interlocking bony spines of our vertebrae that sort of lock each other together. Not permanently, but it allows for some movement, but not a lot. That's another fun word. Those things are called zygapophyses. So again, cervical, thoracic that we see. Here's our lumbar, the sacrum, again the 5 together, and the little bitty bones of the coccyx. They're not really showing the spines. Here you can see some of the spines off of the back. Some of these sort of curved things you see on the side, those are some of the zygapophyses that lock front and back into a movable, flexible vertebral column. And then, in this illustration, here's our normal. There you see how we've herniated. What would be another word that we could use there? Herniated or what? Ruptured. Herniated, ruptured disc. But you see how the jelly is kind of squished out and is pushing on that nerve? Yeah, that's a bad day. All right, so we've got the skull, the vertebrae, now our ribs. So we have 12 pairs of ribs. The first 10 are connected to the vertebral column on the dorsal surface, and they're attached to the front, to the sternum. And that attachment point is via cartilage. But once we get down to pairs 11 and 12, these are not attached, and they are said to be your floating ribs. These typically are the ones that we have fun breaking because they don't have that surface supporting them there on the sternum. Anyone ever broken a rib? Yeah? Breathing, no fun?
Huh?
Breathing is no fun after that? Oh, okay, well. Again, women, y'all have a whole different set of issues that make me so glad I'm a guy. I mean, yeah. So here are our ribs 1 through 10, and you see the blue? That's going to be the cartilaginous attachment from the bony rib over to our sternum. And then here we have pairs 11 and 12 down below. Kind of hard to see 11. It's kind of sneaking in there behind. And then there's number 12. It doesn't necessarily come all the way out to the front. But those are our ribs. Pretty important. What are the important things that are protected by our ribs? Heart and lungs. They're pretty important, right? Can't live without them. All right, the appendicular skeleton, aka everything else. We've got our upper and lower limbs, our arms and our legs, but to attach them back to the body, we have to have these two structures that are called girdles. And again, the utility of calling these things girdles, I don't really understand, because the top one is the pectoral girdle. Our pectorals are our chest muscles. And so our pectoral girdle is basically going to be our shoulder. Versus our pelvic girdle, which is a little more understandable, that's going to be comprised of our pelvic bones. And you can see from our scapula, our arms are attached, and from our hips, our legs are attached. So pectoral first. Fairly straightforward. Shoulder blades, the scapula. And our scapula and the shoulder blade is somewhat stabilized by our clavicle. And that's going to be our collarbone. Now, one of the times when you really see that clavicle break is when you have force on the shoulder pushing it too far forward. A lot of times you'll see either a fall on your shoulder, or a lot of times in football, if you get hit from the side, both sides at once, either one side in the ground and your shoulders come forward, snap. That thing will just pop. But it's important for stabilizing the shoulder. Now, our pectoral girdle attaches our arms. The upper arm bone is humerus. It's not funny, it's humorous. Because if you hit that nerve right in here, what do we say we hit? The funny bone, because it's humerus. Our two bones down below our forearms are the radius, which is somewhat the larger if you look at this end, and then the ulna. The ulna is going to support more at the elbow joint, and the radius supports more at the wrist joint. And then finally we get into the hand. We have the carpals, which are in the wrist. Then we have long bones attached to the carpals. Those are the meta. Meta typically means middle. And then finally we have our fingers, and those are the phalanges. Now, phalanges is a term we're going to use for these most distal of our bones. We're going to have phalanges as our toes as well. So phalanges is either fingers or toes. Now, little preview, when we get to the feet, we're going to have tarsals and metatarsals. Sounds like what's happening in the wrist, right? Carpals and tarsals. How do you keep these apart? Tarsals, toes, and so this has to be the other one, right? Or carpals, up front row, I see you whispering it, say it louder. You drive a car with your hands. So carpals, hands, and just remember whichever one you want to use. Now you're going to remember them both. Ha, tricked you. I made you work harder. Pelvic girdle. And for our purposes, we're going to call each half of our pelvic coxal bones. You actually have several bones that are involved, including the ischium, the ilium. We're just going to call them coxal bones. You can see they're attached in the back to the sacrum. This sort of pyramid-shaped bone that attaches to the vertebral column, the lowest lumbar vertebrae, and the coccyx is on the back. And then we have a fibrous joint right in the front called the pubic symphysis. Once again, ladies, we are really, really glad this is not a fused bone, or the baby's not coming out, because this has to widen and your hip bones move apart to allow. Should I just shut up? Is she about to pass out? She's getting all flush. No babies? Okay. Here's the only thing I can offer. Okay? Remember this. All right? Remember this. Epidural. Epidural. I don't think they'll give it to you after 3 weeks, so you got to wait. No, you have to be dilated to 10 before you get an epidural. I think it's a little bit smaller than that. Now, you're going to have to be along. You're going to have to be along. You're not going to come in if your water breaks in your 2. You're not getting one at 2. I think it might be 5 or 6. Yeah, I think 10. 10. You just about shooting that baby out. Yeah. So, epidural. All right, pelvic girdle attaches our leg bones. Again, femur, tibia, fibula. Now we've got radius and ulna in our arms. For some reason, I can keep radius and ulna and tibia and fibula together. But then I go, okay, which is arm and which is leg? So tibia, T, toes, like tarsals is toes. So if you keep tibia and fibula, know that your lower bones of your leg, radius and ulna, are in your forearm. There's our tarsals, metatarsals, ankle, and foot, and then phalanges make another appearance. Again, these are the smaller bones of our toes, like phalanges were the smaller bones of our fingers.